Today we're talking about rates of change. So if you think in maths, often the rate is indicated by a gradient, or the gradient's a rate. So we've been doing derivatives, so rates of change are to do with the derivative. So just be careful. If we get asked the average rate of change between 2 points, so you might have a graph, say like this, and they want the average change between, say, here and here. They just want to know the average gradient. So what you do is, when you're finding average rate, you just put in the x value into the formula. You start with the furthest one minus the second, and so on. So I'll show you a little bit later. When you want to find the instant rate of change, so what the actual changing is happening in one moment, so just one little point, that's when we find, we use the derivative at that point. So if they said, what's the rate of change at when x equals 3, you just find the derivative at x equals 3. So when you have the derivative, when you find the number for the derivative, if it's greater than 0, we say that it's a positive rate of change. So it's a positive gradient, yeah, if the number is bigger than 0. If it's less than 0, it'd be a negative gradient. Okay, so if you've got the positive one, you say that's an increasing rate. And if you've got a negative one, we'll say that it's a decreasing rate. Okay, so for this question, for the function with the rule f of x equals x squared plus 2x, find the average rate of change. So average rate is when you do the function, so we're going to do f of, and you pick the larger x value, so f of 3 will minus f of 2, and over 3 minus 2. So what you're going to do is, every time we see x, we'll put a 3. So we've got 3 squared plus 2 times 3. That's f of 3 minus, and then we do it with the 2. 2 squared plus 2 times 2, all over 1. So if we tidy that up, we get 3 squared is 9 plus 6, so you get 15 minus 8 over 1. So the average rate of change is 7 for that question. So it doesn't matter in the next one, if you have a look, they're still asking for the average rate of change. We'll still do the same. So it's got two different, it's got a x value that has a pronumeral, but that's okay. So obviously 2 plus h will be bigger than 2, or that's what they're indicating. So we just still do the same. So average rate, just follow the rule. It'll be f of 2 plus h. So every time you see x, you'll put 2 plus h instead, and over f of 2 over, and this will be 2 plus h minus 2. So if we have a look, off we go. So the function says x squared, so instead of writing x, I write 2 plus h squared plus 2 plus h. Okay, so that's the first one, minus, then we're going to do it when it's 2 squared. And all over, that's just going to become h. Okay, so if we tidy all that up, you've got to expand this. This is where it's handier if you know those expansion rules, because that just becomes 4 plus 4h plus h squared, and then we've got plus 4 plus 2h, so that's that bit here, and then we're going to go back to, this ended up being minus 8 all over h. So if we keep tidying all that up, we end up with h squared, the 4's cancelled each other's out. There was left with h squared plus 6h over h. That's a little bit like first principles there. Okay, and now the last one, they want the instantaneous rate of change of f with respect to x. So all they're really saying, we know we find the instantaneous when we find dy dx, we need that, but they're really, this is just a way of saying, can you find the derivative of this function, which we can, which would be 2x plus 2. Yeah, because the function was x squared plus 2x. okay? All right, if we look here is a little bit of a practical application. A balloon develops a microscopic leak and decreases in volume. Its volume is in centimeters cubed at time t seconds is given by the equation below here. Find the rate of change in the volume after 10 seconds and 20 seconds. So the rate of change, we're just going to have to get the dy dx and find it at those times. So if we look at it's actually not dy this time, is it? It's actually dv dt. And if we go look, it'll be negative 10 minus 2/100 t, but we can simplify that to be negative 10 minus t/50. So dv dt, so we've got the rule for our derivative, so we can find the rate of change at any time, and they want when t equals 10, so I'll pop that in. So dv dt at that time will be negative 10 minus 10 on 50, which equals negative 10 1/5. So this is a decreasing rate. So it's decreasing at that many centimeters, cubed per second, and it's a decreasing rate. And then if we look at t equals 20, doing the same, dv dt will equal negative 10, but this time 20 over 50, and we end up with negative 10 2/5, which is also a decreasing rate. So if they ask you to describe the rate, if it's negative, you just say decreasing. Okay, for how long could the model be valid? Okay, because the model is only valid until you have as long as you have a volume or the balloon has air in it. So once the volume is less than 0, so or you could say as long as the volume is greater than 0, it's valid. So we want to know what you want to know is what time does the volume equal 0. So you can probably do this on your calculator, and we'll just put solve, and we'll put 0 for the volume, and we'll put 600 minus 10t minus 1/100 t squared, comma t, and we'll solve for t, and you get t is either negative 1056.78 or t is 56.78. Now we have to know that we eliminate this one because it's a negative time. We don't have negative time. So this is when the balloon will run out of air completely. So when you say when is the model suitable, you just say model is suitable. So from the minute it starts losing air all the way up to when it's got no air, or volume, I should say. So we can write it like that. Okay.